Hello everyone, I'm glad to be here with you today. Let me start off by saying we really are going to do some chemistry here today. The chemicals that we will use will all be chemicals you can find around your house. Now, to realize that is a really important idea. To realize that all that stuff, all the matter around us, all the things we can see, the table here, the screen that you're looking at, is all made of stuff. And that stuff is atoms and molecules, which are chemicals. Okay? So, we're going to make use of some of the common chemicals that you might find around your house that were on the shopping list for you for today. And we're going to make use of these to do some interesting experiments where we can blend some science with some art. So, the first experiment. Primary ingredient here is milk. I'm using whole milk here. I also have some dish soap, although laundry detergent would work, shampoo would work. Okay? And then I also have some food coloring. And any food coloring you have, whatever color or colors you might have. And then I also have some Q-tips. Now mine have a wood stick on them, yours probably paper. If you have the standard ones that you bought at the drugstore, same thing. I also have a plate here, just a styrofoam plate. And I've got a small container. I'm going to use, this is a Petri dish. You probably don't have one of those at home, but you might have something similar, like maybe a small tea plate or something like that, a saucer. Okay? So, let's take a look at what we're going to do. First thing we're going to do is we're going to pour a shallow layer of milk on the plate. I want to cover the entire bottom of the plate. Okay? And I'm going to do the same thing in my little Petri dish here. I'm going to add some milk just to cover the bottom. Okay. So it only takes a couple ounces of milk. Okay? Now, the next step is we're going to take some food coloring. I'm going to do one of these. Let's do red and blue. What I'm going to do is I'm going to add just a drop of each of these right on top of one another, right in the middle. In the middle of that plate. There we go. Oops, I got 2 drops. That's all right. Over here, let's do this one. And let's do green. And let me do red. Okay. Now, we get out our detergent. I'm just going to put a drop on this piece of plastic here. And then I'm going to take the very tip of my Q-tip and just touch it to get just a tiny bit on the end of the Q-tip. I don't need it soaked. And what I'm going to do is I'm going to stick it in the middle and I'm going to push it all the way to the bottom of the plate. And I don't want to mix it though. I don't want to stir. I just want to put it in right in the middle of the food coloring and hold it on the bottom and notice what happened. You can see the colors moved outward and they started to mix and they formed some interesting patterns there. Okay, now I'm going to try the same thing. I'm going to get a fresh Q-tip. I'm going to try the same thing with my experiment that's in this Petri dish here. Same thing. And you see, and look how it was almost like it was pulsing, right? So, let's talk about what happened right there. So, it turns out milk is a pretty interesting substance. Milk is called an emulsion, which is a special kind of mixture. Okay? Some of the mixtures you're used to are things like Kool-Aid, right? Kool-Aid is a mixture, but it's a mixture of water with some sugar, some coloring, and some flavoring. And it's all mixed together and it's all even throughout. We call that homogeneous. An emulsion like milk is not homogeneous throughout because milk is made up of some interesting substances. So it's made up of, the main chemical in milk is water, so there's water molecules. But it also has lots of sugars in it. One of the key sugars that's in milk is called lactose. So that's a sugar specifically that some people who are lactose intolerant, who can't have dairy products because their bodies can't process the lactose, that particular sugar that's in milk. There's also fats in here. Okay? There's proteins, there's vitamins, and there's minerals. Some of the minerals are things like calcium, for example. Okay? Now, it's an emulsion because it doesn't stay as a stable, homogeneous mixture. Over time, if you leave milk sit long enough, the fats will separate out. You might have heard the expression at one time, we used to say the cream always rises to the top. That's because the fats in milk always are going to end up rising to the top because the fats are less dense and because they don't really like water, it turns out. The fat molecules like one another and they get along with each other well, but they don't get along very well with water, which is what makes milk this emulsion. Okay? Now, on the other hand, what we did is we added food coloring to this. Now, food coloring specifically is something that dissolves well in water. That agent, that dye molecule, likes to dissolve in water, so it really likes water. They're water-based food colors. So, the food coloring gets along really well with the water that's in the milk, but not as well with the fats, because the fats don't really like water, so they don't get along with the food coloring much either. So what happens is, when I add the detergent, detergent is a really interesting substance. Detergent molecules are kind of confused. One end of the molecule, and they're big long molecules, and one end of this detergent molecule looks just like fats. And that end of the molecule, because it looks like fats and acts like fats, really likes fats and greases and oils. So it gets along really well with those. But at the end of that long tail that looks like a fat, at the end of that is something called sulfate. And sulfate is a negatively charged group that gets along not really well with fats, but gets along really well with water. So we have this molecule that one end of it loves water. The sulfate loves water. But the other end, the tail of the detergent, hates water. So, what happens in these detergents is, it's going to do some interesting things. So what happens when I put that Q-tip into the milk and the food color in there, is as the detergent goes into the milk, the tail ends of those start sticking to fats. The head ends of those start sticking to proteins and to water molecules. And because of that, it causes all these molecules, and the proteins and fats are pretty big molecules, causes those molecules to move outward, away from one another. And as they're moving, they bring with them some of the water molecules, and those water molecules bring with them the food coloring. And so that's why we see the difference in the colors. And you can see here now that it makes some really interesting and pretty patterns. And again, depending on what colors you use, it'll be different colors. So it's a very interesting way to look at how molecules get along with particular kinds of molecules in some cases, but not others. So in this case, it's about molecules that like water and that don't like water. Now, something else you could do yourself, if you want to do some variations on this experiment, one of the variations is you could put the drops of food coloring in different places, not just the middle. That will do some interesting things. The other thing you could try is we could try adding, after we put in the milk and we put in the food coloring, you could put on top of that milk, you could put a couple drops of cooking oil. Could be olive oil, corn oil, sunflower oil, whatever kind of cooking oil you might have. And because the oil will get along well with the fats, but not with the water, it will stay on top of the water, and it can do some other things to change the patterns that you might see. So that's another variation you could try if you have a little bit of oil there and some help from your parents. Okay, now we're going to look at another experiment, and this one is going to use some of the same kinds of ideas, big ideas, that we talked about in the first experiment. It has to do with how chemicals interact with other chemicals. So, let's take a look and see what we can do here. So the materials for this experiment are some markers, and I've got some washable markers here, and I have one permanent marker. Now in the instructions I just told you to get the washable, and that's because you'll see that the permanent marker won't do much of anything very interesting, but we'll show you that. You also need some coffee filters. If you don't have coffee filters like this, the basket kind, that's fine. You can always use a napkin or maybe a piece of paper towel like this. This will work fine. Okay. Coffee filter is just kind of convenient for me. And I also have just a regular old everyday napkin. Okay. And I'm going to unfold that napkin so it's in Got 4 squares. Okay? So let's take a look. We've got that. The last thing we need is a glass of water. So I have a beaker here instead of a glass because I'm in the lab. But it's filled with water about almost all the way full. A little bit below the top. Okay. So now, here's what we're going to do. We're going to take a coffee filter, and we're going to take our pencil. We want a sharp pencil because the point of the pencil here is to poke a hole through the middle of my coffee filter or my paper towel. Okay? Poke that right through the middle, and now I'm going to set this down, and what I'm going to do is I'm going to pick a few colors of these markers. So let's see, how about, let's do the black marker, and I'm just going to make a dot away from that hole. Make a dot there. I'm going to take, how about green? I'm going to make a dot. Then I'm going to take purple, and purple, instead of a dot, I'm going to draw just a little square. Okay, just a little square, just to make it interesting. And then let's see, how about blue? Let's take blue. Now, this blue is my Crayola washable marker. This other blue that I have here is a Sharpie permanent marker. I'm going to put those blues right next to each other, and let's see what happens. You might be able to see in the camera view here that the permanent blue is a little bit different shade of blue. Okay? We'll also be able to see some differences later. All right, so now we've got that part done. We've made our drawing here on our coffee filter. So now what I'm going to do is I'm going to take my napkin, and I want to tear off half of one of these squares. So just a couple inches wide piece, strip, and then tear down the end of that corner, or yep, that square. And I've got a piece that's a couple inches tall and maybe 4 inches across. And all I'm going to do is roll it up into a nice tight roll. Just roll that right up. And if it's not real tight, that's okay. We can fix that at the end. So roll this up best you can. And what we want is we want it to be a little bit smaller than the pencil. So what I'm going to do is when I'm done here rolling it, I'm going to kind of fold it and squeeze it down. Fold it and squeeze it down so it's small enough to then fit through the hole that I made with my pencil. So I want it sticking through, and I want the wick, this is going to be called a wick, I want it sticking up just above the coffee filter. Okay? So now, a wick. Well, you may be used to a wick used for candles, for example. Now that's a little different kind of wick. That's a wick that gets lit, right, and burns. Now, this kind of wick, though, is used to suck up some water. Okay? So what we're going to do is we're going to put this right over my glass of water with the bottom of the wick sticking into the water. And what's going to happen is that water is going to rise up the paper fibers of that wick. And you can see now that it's making the coffee filter wet, and it's going to spread outward from the middle. So this idea of wicking is really important. Okay? This is what happens inside plants. Okay? Plants use this idea of, the scientific term is capillary action, the way that water will naturally rise up these fibers, okay? And it wicks upward, and in this case, as it gets to the coffee filter, it wicks outward, away from the center, and it's going to keep moving. Now, you can already see something happening with these colors. You notice that the dots, and then the square over here, and then these dots, they're spreading out. They're not all compact as a dot anymore. And that's because they're not just sticking to the paper. They were stuck to the paper, but when the water got there, they had to make a choice. Do they like to be stuck to the paper more, or do they like to be stuck to the water more? And what you're seeing is each of these washable markers here is sticking to the water pretty well. So we find that the dye in these markers gets along better with water than it does the paper. And so as the water moves, the spot, the marker moves. Now notice this dot right here, that blue dot, that is my permanent marker. A permanent marker, on the other hand, is made with dyes that get along really well with paper, but don't get along very well at all with water. So as the water goes, it just runs right through that spot and doesn't do anything to that permanent marker spot. But you can clearly see that it's causing the colors and the dots to move for the washable markers. Now the interesting thing is, if you take a look, you'll notice that this black marker is actually spreading out into different colors. So on the back side here, it's kind of pinkish. It's still kind of blackish in the middle here, but then there's some blue color over here, over to the sides. And so that tells us something really interesting. It tells us that whatever dye they're using in this marker is not a single dye for the black. It's actually a mixture of different colors of dye that have to mix together to make black. Kind of like when you mix different colors of paint, and you can mix those colors together and get different resulting colors, right? Yellow and blue would make green, okay? And that's exactly the trick they've done to get black. So you can see the different colors of dye interact differently with the paper and the water, and so that causes them to separate out. And then over on the other side here, where you saw my little square of purple here, that has become not a square at all anymore. It looks almost as if it would have been two dots that are kind of moving. So, depending on what shapes you might draw on here, you can get different results. So this is one of the things that you could try on your own now. So you could do this experiment. You can use different colors. You can look at different colors and find out which colors are mixtures of dyes and which ones are single dyes. You might have some races between dots to see which dots move faster. And you can do some really interesting pictures and make different lines and so on instead of just dots. And you could add a lot and make a really pretty picture on this. And if you use the basket filter like this, it's already arranged in kind of a flower type form, so you could fold that up and make interesting things with interesting colors on the outside. And you could make it look maybe like a flower. And you could even put a stem on it, maybe with a pipe cleaner or something like that if you would like to. So you can really use ideas from chemistry to make some art. So I hope you enjoyed those two experiments, and I'm looking forward to answering some questions for you after these experiments are done. So I hope you enjoyed it. Maybe next time we can try some other experiments. Take care.
Hello everyone, my name is Eric Eichhoff, and I have the pleasure of serving John Carroll University as the Associate Director of Alumni Relations. I'm excited that you have decided to join us for JCU Jr, our new program aimed at providing our youngest members of the Blue Street community with interesting and engaging programming. This summer, we are offering 5 sessions for you to enjoy, from baking to space exploration and manatees to poetry. We truly have something for everyone. Today, we focus on chemistry. We've also created an activity book similar to the National Park Service Junior Ranger program for you to use. You can complete the activities found in the workbook, and those who do will receive a special certificate and a JCU sticker. You may download the activity book on the Alumni and Friends website at jcu.edu/alumni. It is now my pleasure to introduce to you Dr. Mark Waner, Ph.D., Associate Professor of Chemistry and Director of the Woodrow Wilson Teaching Fellows Program at John Carroll University. Dr. Waner is a member of the John Carroll University class of 1991. Following graduation from JCU, he continued his studies at Michigan State University, where he developed an interest in science education. This interest took off after joining a group called Science Theater that put on science programs at schools and community events throughout Michigan. After completing his PhD in physical chemistry, he taught for a year at Spring Hill College, the 3rd oldest Jesuit school in the US, before being hired at John Carroll in 1999. At JCU, he has taught chemistry and science education coursework and continues to do science programs for kids. Please join me in welcoming Dr. Mark Waner.
Hello, everyone. Thanks for the introduction. I'm really glad to be here, and I'm looking forward to doing some experiments with you today that will kind of focus on the intersection of chemistry and art. So that's where we're going to be going into the lab in a bit.
Awesome. Okay. Let me pull up the questions. Mark, those were great experiments. Thank you again for taking some time to do those with our families. We did have some really great questions from some of our kids who registered for the program, and I wanted to share some of those with you and get your thoughts. So Catherine, who is 11 in Toddville, Iowa, was wondering what kind of jobs are available to those who have a degree in chemistry.
Wow, that's a great question to ask, and there's actually a lot of jobs available. One of the things about somebody who studies chemistry is that they have a training across a variety of areas, and you develop a lot of skills besides just traditional chemistry skills. So we have a lot of students that go on and do really interesting things in medicine. They do interesting things more broadly in healthcare. We have lots of students that go into traditional chemical industries. Like here in Cleveland, one of the big industries is with paint, with Sherwin-Williams, for example. So that's obviously chemistry, but there's a lot of other chemistry jobs that a lot of people don't really know about. Like, for example, there's a company in Ohio that makes really high-end candles, and they hire chemists as well because they need the chemists to design the dyes that go into the candles and all of the scents that go into the candles so that they smell right. And so it turns out chemists work at a whole lot of different companies, from food companies to candles. They work in law. They work in all different kinds of areas. That's one of the things I really liked about going into chemistry, is that I had a lot of opportunities to try different things.
Thanks, Mark. So Miles, who lives in Buffalo, New York, is age 7, and he wants to know, what is your favorite element and why?
Oh boy. Well, that's a hard question because there's so many really interesting and cool elements. But as I think about it, I would probably say my favorite would probably be oxygen because of how important it is. And it's also interesting because we're all familiar with the oxygen that's in the air around us, right? And the air around us has about 21% oxygen. And without that, we wouldn't live. So it's super important, right? But what a lot of times people don't realize is that another form of pure oxygen is ozone. And ozone is actually toxic to us. And so we have to be careful when there's high levels of ozone, especially people with lung problems have to be careful going outside when there's high levels of ozone. And then you may have heard about the ozone layer, and that's a layer in the atmosphere that's made of ozone, and it protects us from the really high energy ultraviolet light that can cause sunburns and skin cancers. And so I find it really interesting that oxygen can be really, really important to us and necessary to live, but also could be toxic in one sense, but also really helpful to us at the same time. So it's one of those elements that's, to me, kind of really interesting.
Makes complete sense. I never thought of it being in all those different ways. That's a pretty
Yes.
cool way to look at it. So Brody has 2 questions. So Brody's age 9 from Winter Park, Florida. The first question is, did you like science as a kid? Is this something that you have always loved? And then his other question is, do you have a favorite chemical?
Okay. Well, I did always like science. I liked other subjects as well. One of the subjects I really enjoy besides chemistry and science is history, for example. But I always really liked science. Now, what's interesting though, in my case, is when I was a kid, I really liked things like paleontology, looking at fossils, geology, looking at different rocks and minerals. I loved that stuff. As I got a little bit older, when I was maybe 10, 12, I was really into electronics. And so I used to go to a place that doesn't exist anymore called Radio Shack. And we would buy electronic parts and we'd buy kits to make radios so that we could listen to airport conversations, or we'd build things that would make things light up or little alarms. And I just got really fascinated by electronics for a long time. So it wasn't until I got much older and I got to college when I actually found out I actually liked chemistry. And even when I started at John Carroll, I wasn't going to study chemistry. I didn't think I would like that. I was going to study physics and engineering and math because I really liked those things. But then what I ended up finding out is I could do chemistry and I could do physical chemistry, which is where chemistry kind of intersects with math and with physics that I also liked. So it was a way of putting all those interests together.
What's your favorite chemical?
So my favorite chemical, I would have to say it would be the chemical I've been studying for the past 22 years. And that is a chemical called streptavidin. And that's the name of a protein. It's a protein that's really important in biotechnology. It's used in all kinds of different biotechnology and hospital tests that are done. And it's a really cool chemical because it binds a small molecule called vitamin H or biotin. And so in my research, that's what I study. I study this protein and what happens to this protein when it binds this really small molecule. And it turns out to be a really complicated molecule. And so it's led me to all kinds of interesting experiments that I've been able to do over the last 22 years and publishing papers on just this one protein. It's really kind of cool.
Huh. Do you remember how you found out about that protein? Like how did you learn about that one?
That's a great question. So I actually first found out about it in graduate school. So for the longest time, I didn't really study any biological molecules. I focused more on traditional chemistry, not as much biochemistry. But once I started looking at proteins, this was such an important protein in so many areas of biotech that it just became interesting. But at the same time, I also didn't think it would be something I'd study for 20 years because it was such an important tool. I figured, well, everybody knows everything about this because it's a great tool. But what I found out was they knew what it did. They didn't necessarily know how it did that. And so that's where I've gotten lots of interesting questions out of just going back and saying, well, that's really cool, but why and how?
That's pretty awesome. That's really cool.
It's a lot of fun.
So speaking of fun, we didn't get a name with this one, but a wonderful kid submitted this question. What is your favorite part of your job?
Ooh, favorite part of my job. Wow. There's so many parts of my job that I really like. I guess probably my favorite part is that I get to teach students. And I like to say that broadly because normally I teach adult students and I love that. But I also like that I have the opportunity to be as involved in science education as I am so that I can go into kindergarten through 12th grade classrooms and talk to students of all ages. So the fact that at this level, at this job, being a professor, that I can interact with and talk about chemistry and talk about science with a wide range of people is just, it's a lot of fun. I really enjoy getting to know lots of different people of different ages and different backgrounds.
I think it's one of the great things about working at being associated with a college like John Carroll is that you have that ability to connect with so many wonderful people.
Absolutely.
Okay, we have another Miles. This one, he's age 12 from Strongsville. How does chemistry involve math?
So a great question. As I mentioned a couple minutes ago, I really like math and I really like physics as well as chemistry. And that's why I studied physical chemistry, because that's really where a lot of math and physics intersects with chemistry. But even more broadly than that, anybody that studies chemistry has to know a certain amount of math because there's a lot of mathematical thinking. So it's a lot of mathematical thinking and problem solving that goes into chemistry. So you have to be able to work with numbers, you have to be able to work with data. Some of it's very visual too. So you learn a lot in math about graphs, for example, right? And so graphs and tables and looking at data and showing different ways to represent data is part of math. And that's really, really important to chemistry. So if science is something you're really interested in, math is always going to be a part of that because math is really important to all the sciences. But in particular chemistry, a lot of algebraic thinking. So when you get to algebra, the kind of math that you learn there is really, really important to chemistry. Later on, you might get into calculus and statistics and some of those things as they apply to chemistry. But I would say a lot of it is really starting at that algebraic thinking level. And you start getting into those algebraic thinking. This student was 12, you said? So he's probably already had some math in school that they're not necessarily calling it algebra yet, but you've probably had exposure to a lot of this algebraic thinking and thinking about relationships of numbers. So that's really important stuff and certainly very necessary to study chemistry.
That makes complete sense. That makes complete sense. And then the final question, and I know this is something that actually happened in my house earlier this year, and I'm sure a lot of kids have the same question. It comes from Lily. She is age 10, again from Strongsville. How does the baking soda volcano work?
That is a great question. That's a classic experiment, right? Mm-hmm. So a lot of people have done that one. So what's going on there is the baking soda has what's known as bicarbonate in it. And you hear that little prefix there, bi, in front of the carbonate. So any of the carbonates, whether it's a calcium carbonate, which is one of the main components in limestone, or bicarbonate, like is found in baking soda, it has some carbonate in it, which is carbon that's connected to 3 different oxygens. And so I remember back when I said oxygen is one of my favorite elements, it's involved in so many important molecules, and this is a great example of one. So carbonates, when you take a carbonate and you put it with acid, the acid, which is the vinegar, will react with it, and it releases carbon dioxide. And so all that bubbling is this really rapid release because the reaction happens really fast. It's a rapid release of lots and lots of carbon dioxide. It's the same stuff that's in your soda pop. When you open up your soda pop and it pops and you start seeing bubbles rise, that's carbon dioxide being given off. And so that baking soda volcano is just a really, really rapid reaction releasing carbon dioxide from that bicarbonate. It's really cool. And there's some really good experiments you can do with that. Besides just the volcano, there's some cool experiments you can do to extend that. So maybe that can be another session later on.
Yeah, that'd be wonderful. One follow-up. I know you just showed us some amazing experiments in your lab. Are there places that you direct kids to on the web to go find out more about chemistry?
That's a great question. There's a lot of really good sources out there. I'm trying to think. I haven't kept up with all the places. One place that I know has some good stuff, if you particularly like chemistry and some of the stuff we talked about, you can go to the American Chemical Society website, which is acs.org. If you search under their tab for education, you can find all kinds of information. They have lots of great experiments for kids there. In fact, they have a good video of one of the experiments that I just did earlier in the video. So that would be a great place to go if they really liked chemistry. There's a lot of other great places, a lot of the good science museums. So whether it's the museum here in Cleveland, whether it's a natural history museum here in Cleveland, a good site nationally is the Exploratorium out of California, that science museum. They have lots of great stuff on their website.
Awesome. Well, Mark, thank you again so much for taking time to share your expertise and love of chemistry with our Blue Streak families and our community. We truly appreciate it. We are incredibly grateful that you are a member, not only of our faculty, but of our alumni community. We are just very fortunate to have you. For all of our families who participated, we hope you enjoyed it. There are other sessions as well. We hope you take part of those too. And if you have any questions, please contact us at alumni@jcu.edu. Thanks and have a wonderful day.
Sounds good.